In this lesson, we're going to be talking about the attributes of a quadratic graph. By the end of this video, you should be able to identify attributes of a quadratic graph, including domain and range, x and y intercepts, zeros, maximum and minimum, and the vertex. When we're talking about quadratic functions, these are the functions that give us a parabolic shape, or this parabola shape. We see them in the real world in lots of different things, whether it be in architecture, whether it be in movement. Any type of movement or shape that gives us this parabolic shape would be considered a quadratic formula, or quadratic equation. Now, obviously, nothing is going to be perfectly quadratic when we're talking about real-world situations, but if the general shape is this parabola, then we know that it's a quadratic function. When we're talking about quadratics, we're going to look at the difference between quadratic equations versus linear. When we talk about a quadratic equation, when we graph it, we're going to end up with what's known as a parabola. This is that U shape that we see. So when we're looking at a quadratic, we get this U shape. Versus when we graph a linear, we get a line. The standard form for a quadratic formula is y equals ax squared plus bx plus c. Whereas in linear, it's ax plus by equals c. Notice that the exponent of the quadratic is 2, meaning that it is a degree of 2. If the coefficient of a, when we're talking about the standard form for a quadratic function, if the coefficient of a is positive, then we know that our parabola is going to open upwards. So I like to think of it as a smiley face, right? If something positive happens, then you smile. So in our parabola, if it's positive, if a is positive, it's up, like a smiley face would be. If the coefficient of a is negative, then the curve opens downward. And again, thinking about it in terms of mood, right? If something negative happens, you tend to frown. So if it's a is negative, the curve is going to open downwards. When we talk about the parts of the graph, one of the parts of the graph is what is known as the minimum or the maximum. Now, depending on which way your parabola or your quadratic graph opens, whether it opens up or whether it opens down, you're either going to have a minimum point, so the lowest point on your graph, or the maximum point. This minimum or maximum point is also known as your vertex, the vertex of your graph. So the minimum or maximum is also referred to as your vertex. Now this is going to determine your range. Your minimum and maximum value, or your vertex, is going to determine the range when we look at the y values. Then we have what's known as the axis of symmetry. Something that's important for us to realize and recognize with quadratics is that when we graph them, their graphs are symmetrical. The parabolas are symmetrical. So that means on either side of your vertex, either side of your axis of symmetry, they should be symmetrical. They should be the same on both sides. They should be mirror images of each other. So your axis of symmetry is the fold line. It goes through your vertex. And when we're representing the axis of symmetry, because it's a line, we write it as an equation. The equation is going to be x equals wherever the line crosses on the x-axis. Domain and range are also other attributes that we look at. Domain would be all of the possible x values that you could have. Range would be all of the possible y values. And when we're writing out domain and range, it can be written as either an inequality or it could be written in interval notation. And we'll take a look at that as we go through the examples. The x and y intercepts are your other two features that we have. So these are going to be the final features that we look at. X-intercept, remember, is where the line crosses, or is where your graph crosses the x-axis. And we represent that as ordered pairs. The y value in each of the ordered pairs would be 0. Your y-intercept is where the graph crosses the y-axis. Again, we write it as an ordered pair, but this time the x value would be 0. And then your zeros are where your graph crosses the x-axis. This is the same thing, or very similar to our x-intercepts, except when we're listing out the zeros, we only list out the x values, not the entire point. So if we take a look at number 1, we're going to look at the domain and the range. Remember that the domain is all of the possible x values. So we're looking from left to right. We're looking from side to side. We look at our graph and we say, hey, where does it start? Well, because I have this arrow here, this arrow is telling me that it's going forever in this direction. It's going forever to the left and it's going forever up. It's going forever in two directions. So because it doesn't start anywhere, we would say that our domain starts at negative infinity. And where does it end? Well, it doesn't end. It's going to keep going forever to the right. So we see that it's going forever to positive infinity. So one way to represent our domain is to say negative infinity is less than x is less than infinity. We put the variable, we put x, because x is our domains, all of our possible x values, and we're going to write it as a compound inequality. So our domain here would be x is greater than negative infinity, so it's all the values that are larger than negative infinity, but it's smaller than infinity, so it's all the values that are less than infinity. This will include all real numbers. So because this includes all real numbers, the other way that we could write it, and the more accurate way to write this would be to say all real numbers for our domain. Now, we decided we could write it as an inequality, but we could also write it as in interval notation. So as we're writing it in interval notation uses a set of parentheses and brackets. The parentheses are not including the value, whereas the brackets are. Now we never include infinity when we're listing out our values because infinity is not an actual number. It's just telling me that it's going to go on forever. So because we know we start at negative infinity, because it doesn't actually start anywhere, we'll do parentheses, negative infinity, comma, and then where we're ending, which is infinity, parentheses. We look at the range. The range is going from bottom to top. So our range goes from bottom to top. So from bottom to top, we start at 0. So my range starts at 0. And it doesn't stop. So it's all of my values that are larger than 0. So my y values are anything that are greater than or equal to 0. Again, we could write this in interval notation. We start at 0, so we always go from least to greatest. This time I'm including 0 because it's a point on the graph, so I'm going to use a bracket to include, comma, we don't end, so it goes on forever into infinity. So infinity and then parentheses, again, we don't include infinity. The vertex of this graph is at 0, 0. The vertex is where the value, where our turning point is. So there's our vertex, which is 0, 0. Our axis of symmetry is the line that goes through our vertex that cuts our graph in half. And it's x equals, wherever it crosses on the x-axis, so in this case, x equals 0. Our zeros, where it touches the x-axis, it touches it at 0. The x-intercept would be 0, 0. The y-intercept would also be 0, 0 for this graph because it crosses at 0, 0. And we have a minimum point here, and that minimum point is the same as our vertex, which is 0, 0. Let's take a look at example number 2. Again, our domain and range. So our domain, again, we're going from left to right. Where do we start and where do we end? The arrows tell us that we don't start and we don't end, so I could write it as all real numbers to show that any number will work for my domain. Or if we're going to write it in interval notation, that would be negative infinity to infinity. Remember, the parentheses are not including the values, and we never include infinity. Our range, we start at 4, and it's everything that is greater than that. We're going from bottom to top. So our range would be y is greater than or equal to 4. All of the y values that are larger or equal to 4. Remember, if we're going to write it in interval notation, it would be 4 bracket, because we're including 4, to infinity because we're not stopping. Our vertex would be, again, where our graph turns, so that bottom part, that would be 0, 4. Our axis of symmetry goes through the vertex. Where is our graph symmetrical? It's symmetrical at x equals 0. Our zeros Well, because it doesn't cross the x-axis, there are not any zeros, which means that there's also no x-intercepts. The y-intercept where it crosses the y-axis is at 0, 4. We have a minimum point, and that minimum point is the same as our vertex, which is at 0, 4. Sample number 3, our domain, again, if the arrows are not there, and we're not looking at a real-world problem, it's indicated that it's there. Our domain, again, for this one goes from negative infinity to infinity, so that's all real numbers. Most of the time, we're talking about quadratic graphs, the domain will be all real numbers, or negative infinity to infinity. Our range this time, we're starting at 9, is our vertex, right? And it goes down. So we want all the values that are less than or equal to 9. Now, when we're writing in an interval notation, remember that we're going from bottom to top. So it's all of the values from negative infinity all the way up to 9. We're including 9. Our vertex, they tell us, is at negative 1, 9. Our axis of symmetry goes through our vertex. And that's at x equals negative 1. Remember, axis of symmetry is an equation, and x equals equations. We have 2 zeros here. Our 2 zeros are negative 4 and 2. Our x-intercepts are negative 4, 0, and 2, 0. So same as our zeros, but now we're writing them as points. Our y-intercept is at 0, 8. This crosses the y-axis. We have a maximum point this time, and that maximum point is the same as the vertex, which is at negative 1, 9. Looking at this real-world problem, we see that a diverge follows a path that is in the shape of a parabola, and we see that in the image. Suppose the diverge foot reaches 1 meter above the height of the diving board at its maximum height. So we know that this is our max, also our vertex, which means this line is our axis of symmetry. At the time, the diverge foot is also a meter horizontally from the edge, and it's wanting to know what's this total distance right here. Well, I know that if this is the axis of symmetry, and it makes it symmetrical, if this length is 1 meter, then this length has to be 1 meter, making the whole length 2 meters. The reason why it's 2 meters is because parabolas are symmetrical. These are the key attributes of a quadratic graph.